Thank you for inviting me here. Like, I'm super excited. I think this is kind of projects that I'm really interested in participating. And for the audience, this is the first time I'm going to be sharing this content and this project that I'm going to be talking about. So I'm super interested in getting feedback on the amount of details that I'm giving and kind of like, I'm interested in knowing if the message is getting across. And of course, if this is something that you find valuable, because I'm interested in maybe then expanding this talk and giving it into different audiences. All right, are you all seeing my screen?
Yeah, it looks good.
Cool. So today I'm going to be talking about the challenges of scaling databases. And specifically, I want to focus on a case study, like a very specific project. And just like to set the stage, like the agenda of the day, like I'm going to give like a quick intro about what I do. Then we're going to talk about databases at Slack and a specific technology that we use to scale our databases that is called Vitess. And that will be kind of like a historical context so you know what I'm going to be talking next. And then last, we're going to go deep in this case study of how we migrated what we call the legacy shards, that you will learn more about them later, and it's these projects that we call BIFOs. Vitess in front of legacy shards. Like, this is something that Jonathan will also relate. Like, there is no project in doesn't have like an acronym, and that is people who likes that and people who hates it. But anyways, the name of the project is BIFOs. And last, we'll have some chance to get like Q&A. So I'm not going to spend much time because I think Jonathan did a really great intro about myself. And in case you don't know what we do at Slack, we are an enterprise communication platform. Our mission is to make people's working life simpler, more pleasant, and more productive. And at the beginning, like, you could say that it was kind of like a chat for companies, but it has evolved into more like an operating system for your company. And specifically, I work within the core infrastructure and data stores team at Slack. And when you ask me, okay, what is it that we do? Like, what is our role? And if I can summarize it in just like one phrase, I would say that at the end of the day, what we're doing is moving bytes around from one machine to another without no one at the customer level noticing, and enabling the business to succeed while we do that. And this relates to what Jonathan was speaking earlier, that at the end of the day, infrastructure teams are the foundation that allows a company that is going through rapid growth and rapid, like, facing rapid scaling issues to continue to operate without the customer noticing that these challenges are happening. So in a nutshell, like, we do our job well if no one notices that we're doing our job. So it's kind of like an interesting role to be in this kind of companies. And I think the thesis that I will be building in this presentation is that at the end of the day, we are just moving bytes around. So without further ado, let's dive into databases at Slack. First, just wanted to share a little bit of stats of what is the scale that we're speaking here. In terms of like the users, we have around 12 million daily active users. And at peak time, imagine like the amount of traffic that this generates, like 12 million people using our application. And when you see it from the database perspective, this translates to around 65 billion queries per day. And in terms of storage, we have around 9 petabytes of data. This is thousands of database servers that are behind this to support this kind of like traffic. And I want to pause here to kind of like grasp what 9 petabytes of data means. If each megabyte were a meter, we will have enough data to send like a rope from the Earth to the moon 25 times. So it's like a lot of information that we have to store to support the needs of our application. And to make sense of like how, like, what are the kind of challenges that we have, you need to understand a little bit like what is the architecture of Slack, at least in a very like basic way, like the main building blocks. And Slack is a very traditional application. It's what is called a LAMP stack, or at least it used to be. There is Linux, Apache, MySQL, and PHP. And at its foundation, it was a monolith app that contained like all the business and domain logic for the application. And then we have thousands of what we call shards that were storing the information for the teams. And the way that this worked is that we had this database that we call the mains database that contains the metadata about in which shard the information for a given team lives. So when the application, let's say, was bootstrapping, it will go to the mains, it will ask, hey, my team ID is 123, what is the shard where that team data is stored? And then from that moment on, it will just talk to the team. And what you see on the left, it's a cluster of databases that we call OCS, that is data that doesn't really belong to teams. We just put it there. You can think of it as the kitchen sink of the data or Slack. And this was the original architecture. And it was very simple, and it served us well. Like this kind of like way of modeling our application allow us to scale from the beginning of Slack in 2012 to around 2017. However, this model started to show some limitations. And I'm not going to enter into too much detail in those limitations, but one particular thing that we can speak to grasp what was one of the problems is that this architecture is prone to hot spots. So imagine that you have a team that is really active, and that team has could have hundreds of thousands of users. Like for instance, recently, Amazon started to use Slack, and Amazon has millions of users. So the shard for Amazon was going to be really hot. And what we started to see as we scale is that we had a few shards that were like really, really hot, and then a long tail of shards that just didn't have like that much traffic. So the usage was very uneven. It was almost like a logarithmic scale, the way that the distribution of usage and load was between our fleet of databases. And this represented a kind of like a threat, because what happens when a single team doesn't fit in the biggest available hardware? Like this was going to be kind of like the end for the way of scaling our application. So we embarked in a project to say, okay, what is the future of databases as Slack? And we came up with like these requirements that are also kind of historical of the context of Slack as a company. Like we didn't want to stop using MySQL because we had like a tons of operational knowledge. And the other thing that relates to the hotspots is that we needed to provide flexible sharding. So it was easy, depending on the domain of the table, to change how you were sharding it. We didn't want it to be tied just by team ID. That was the case that I showed earlier. So for instance, like messages in a channel, it might make sense to shard them by channel ID instead of like team ID. And that will distribute messages evenly across channels in all Slack, not just in a given team. And of course, we needed it to be horizontally scalable and highly available. And that's how we run into Vitess. Vitess is a technology that started at YouTube, and it allowed YouTube to scale. And what it provides is that it's an abstraction that looks as if you're talking to a giant MySQL database, but behind the scenes, like you can have thousands of charts. And it provides this requirement that we had, that you have the granularity of like case by case, like table by table, decide how you're going to be charting that table. And again here, like if you're curious about Vitess, like we can maybe like later on, like just do a talk about this technology. Like as part of my role, like I have become a maintainer in this project, and I would say that maybe like 80% of my time at Slack, I spend it contributing to this project and developing features that help us at Slack. But in a nutshell, the architecture of Vitess looks like something like this. That you have this component that is called VT gates, that it's a proxy, or yeah, it's a layer that you put in between the charts and your application. And then from the application perspective, these VT gates just look as if you're talking to MySQL server. But VT gates are stateless, that you can scale those easily. And then you have the charts below that. And then you also can see that at the end of the day, like these charts continue to be just MySQL with an extra component that Vitess uses to provide some extra features that are not relevant for the purpose of this talk. But you can see that, I don't know, like this architecture like hides the complexity of how your topology and the layout of your data is going to be. And then from the application perspective, is just as if you're talking to a giant MySQL database. And we use this, and if you want to learn more about how we were migrating, like originally like these tables, and let's say how we went from 2017 to 2020, there are talks that we have given in other like places, and you can go and look at those if you want to learn more about this part of the migration. But the part that I want to focus today is that when you see like this migration, like we started in 2017 and we were moving like slowly, like this is where July 17, I joined Slack. We were not, we didn't have Vitess in production at the time. And then little by little, as we learned how to operate the system, we started to migrate. 2018, we were around 25%. And this was kind of like painful process that took us almost 3 years to get to 75%. And the part that I want to share today, the specific project, is how we got from the 75% to 100%, which is a very interesting project in this kind of systems, because migrating the long tail in legacy systems is always a challenge. And most of the time, companies decide just to pay that, you would say like operational burden of having like two systems and live with two systems, because certain parts are just hard to migrate. But at Slack, like for many reasons, we decided that we didn't want to live in that world, and that we wanted to make sure that we could finish this migration and have like everything running on top of this platform, and have a unified platform that allows us to scale in the, like what we're hoping for is at least 10 more years. So this is where Vitess in front of legacy shards enters in the equation. So what happens is that we were able to migrate 70% in around 2.5 years. And when you dig into what it meant to migrate 70%, we did it by migrating the most complicated tables, the tables that contain like the most important parts of the domain. When you think about Slack, that's going to be messages, files, channels, channel members, like the kind of like core data that supports our application. And migrating each of those tables was a super complicated project, like many quarters, like many engineers. And at the end of the day, it was not really a migration. What we were doing was re-architecturing the application. And basically, this was because we were focused on going from this team-based model to a model that was more flexible, depending on the specific table. But then the last 30% was around 150 tables. And all the process that we designed to migrate the first 10 tables was optimized to be a re-architecture. So it didn't work. Like at best case, like an easy table that we didn't want to even change the sharding key, it was taking at least a month of an engineer like working full time to move it. So imagine this, if we wanted to use the same process for this long tail, it was going to take 12 years of engineering time to finish the project. And of course, like, this was not feasible. And I always like to think of problems like visually. So if you want to, if I would like to summarize like how was the migration for the first 10 tables, it was something like this. Very involved, where you have a person who is looking like really carefully And then when it moves the thing to cut over, things move a little bit, but then you're able to uh, finish and, I don't know, like migrate the table, like very involved. But what do we do with the rest of the tables? Like the new challenge was like really different, and we did really different, and we couldn't spend like this amount of time. So what I'm going to describe here is how we solve this problem. And this simple framework that I'm showing you here, I think is something that you could replicate in different environments. What we did at Slack is with some specific technologies, but at the end of the day, I think the framework itself could be general. It's general. You can use it in different contexts. And what we did is that we focused on migrating entire clusters, not just, sorry about that, not just tables. We wanted to go and take one of these legacy charts and move them entirely to Vitess. And we did this by a series of steps that I'm going to enter in detail, but basically it was 4 steps. First, restore and upgrade, then synchronize, then validate that the data was the same, and then migrate. And what is the challenge here? When you look at the MySQL topology of our legacy charts, it was something like this. First, it was running in MySQL 5.6. This is the version of MySQL that we were running on a legacy system. Then we were using this kind of like replication that is called statement-based replication. I can enter in more detail if you have questions about this at the end of the presentation, but this is just important to keep in mind because it's the configuration that this server had. Then another important thing, and the people who is familiarized with MySQL will probably raise their eyebrows, that this was something very specific to Slack that we run in a master-master set. And what this means is that we have like 2 pairs of servers, and both of them like replicate from each other, and they both accept writes from the application. And by definition, this is kind of like a risky model to operate because you can run into inconsistency issues. However, like we solved that inconsistency issues with logic in the application where in the happy times, the application only prefer one of the sides based on the team ID. But when one of these hosts dies, the traffic like swings to the other one. And basically it was an architecture that was gears not towards consistency, but towards being like highly available. And it was like something like kind of like risky, but it worked. It like mostly worked for us. But then the last important thing about the configuration is that it was using async replication. This worked, but it created like some challenge at the level of operating cluster because not that many companies are running MySQL in this way. So a lot of tooling we had to build in-house to support this topology at the MySQL level. And Vitess had a more traditional MySQL architecture. It was 5.7, it used a different kind of replication protocol. It was master replicas, that was a more standard setup for MySQL cluster, and you can have like n replicas per shard, and it was using another kind of like setting that is called semi-sync replication. And the important takeaway here is that transitioning from this left side to that right side, like you cannot do it in place without putting at risk the topology that we had in the legacy architecture. So basically, it was not an option for us to try to say, oh, let's upgrade MySQL in our legacy charts. Let's then change the replication to be row-based. Then let's change to not be like a master-master. Like doing that in thousands of servers, it was going to be a dance that was like too complicated to be able to do it like safely and not putting at risk having like outages when we do that. So to migrate this entirely and go from that topology to the new one, I want to use another like visual analogy. If the other one was like a simple, or not simple, but like really like tight coordinated migration, this was going to be something like this, where you needed to have something that was like working like flawlessly at the level of automation, and then move the entire thing without having like a single glitch. And the steps that I described earlier, like how they look in detail, are something like this. First, we start a fresh Vitess MySQL shard with the topology that you have in Vitess, and we seed it from a backup from our legacy system. And we bootstrap this shard, and it will have the data at some point in time. Like this is not live, like this is disconnected from our production system. It's just an empty shard in Vitess that then gets a backup from the legacy. And at this point, we kind of like solve the problem of like how we migrate from the legacy topology to the new topology, because we do it like safely outside of the context of the application, and we put it at a given point in time. But then we needed to solve the challenge of, okay, this is a backup that is in the past. How we synchronize this backup with the live data and the live traffic that the legacy charts are taking. And for this, we did this kind of like interesting project where in Vitess, we created like this process that we call VT shovel, because it's shoveling data from the legacy systems to our new system, that hooks into the MySQL replication protocol, and it understands what was the last position that was in the backup that we have in Vitess, and it starts replicating like that data. And it starts moving the data from the legacy system to the Vitess shard and puts those two database clusters in sync. Of course, in sync, having like, there will be a delta by definition because there could be lag, right? Like it will take some time to move some of the data from the legacy to the Vitess side. But then at this point, we have the two systems and they are kind of in sync. And then we needed to build the confidence that this was going to work, and that from the application perspective, if we were to migrate to start serving traffic from Vitess, things were going to behave the same way, both at the, even like just, are these queries, once we change the MySQL version, once we change that now they're on Vitess, once we change basically the entire system behind the scenes, are they going to continue to work? And what we did to solve this problem is that in our application, in our monolith, we implemented a system that allows us to read from both of them, and we call this like dark reads, and we are able to compare the results. And we are able to see, oh, what we read from Vitess is going to be exactly the same thing that we read from our legacy system. And this step, like I'm showing here, like, okay, just one slide, but we spent here months, you know, like in a subset of the thousands of databases that we felt it was a representative sample of the traffic of Slack. And we ran this, and we run these comparisons, and we build a whole like analytics framework to understand that things were matching and that things were in a good state. And of course, in this step, we did find like some queries didn't behave the way that we expected. So that required like doing like just like small changes in the application that make sure that things were going to work once we got over. But we were able, like our theory that it was possible to migrate everything in bulk was validated. And then the last steps were just cutting over the traffic. And the way we did this is that we also built this kind of like state machine in how we route traffic to our databases, that we were able to transition from, first, we told the application, hey, forget about the master on the legacy shard, just send traffic to one side. And at this point, like this was like pretty fast. Like this is an operation that just happens in the matter of minutes, checks that things are healthy, that everything that was on the left side replicated to the right side of the master pair, we check that the BT shovel was in sync and all the data was replicated. And last, when everything is like looking like good, we say cut over and start serving traffic from Vitess. And here, you could see, or you could say, oh, but what happens with the data that was in flight and that was still replicating while you swing the traffic from the legacy to now route through Vitess? And it is true that in that case, it is possible that we could run into some small inconsistencies because there could be a race between the data that is replicating through VT shovel and the data that now was sent to Vitess through VT gates. But when you think about it, that was already like true in our legacy system because of the fact that we were running this master-master setup that was also prone to inconsistency. So we didn't change the fundamentals of the system, and then that inconsistency, we assumed that it was going to be safe, and in fact, it was. And then at this point, we had all the traffic now going to Vitess, and we could get rid of the legacy system. But we needed to do this more than 1,000 times, no error, and zero downtime. So in order to do this, automation was key. Like, this was a process that it was, to me, it was the closest that I built to have like a real, I would say like a factory. It was a full automation where you have a queue of shards that were going to be migrated, like you put it in this queue, you start moving to this process of these steps, they get to the step where they're validated, and then they cut over, and at almost like no human intervention in all these steps, because otherwise migrating like 1,000 shards, it was not going to be feasible. And just to close, did it work? It did work. And this was a big bet because no one in the company at Slack had tried something like this before. And it's actually like not, like we didn't find like any literature or any people that have done it in this similar way of like migrating entire clusters, even in different contexts. So there was a lot of uncertainty. To provide like some color on that, we have been migrating in the last quarter, and we did like most of the shards, like this 70% of the legacy shards, like we did it in 4 months. But in order to do that, it took us almost a year of design, validation, like building the confidence that this was going to work. So there was like a big risk, but it paid off. And then, as you can see, like from even like all this project and like all my history as Slack, at the end of the day, I just been moving like bytes around from one system to another, but with the challenges that come of doing this at scale, with zero downtime, and in a way that is transparent to our users. And that's it. That's what I had to share today. And if you have questions, I'm here to answer them.
While we wait for more questions, I'll ask a first one, which is more not so much a technical question and more like a philosophical question for you. Mm-hmm. I wondered the question, like the overarching question that I have in my mind is, I wonder what's the impact on Slack's kind of viability as a business and as a technology. Mm-hmm. Like what impact Vitess or equivalent services have on the viability of something like Slack? Meaning, you had this massive need to scale, and you went out into the market and you found this thing that YouTube, which is a private company, mm-hmm. Built all this kind of amazing open source infrastructure that you could use to make this change happen. So I wonder if you have, that's like the overarching question that I have, like how impactful it is. And I think that the way, that was not a very specific question. So I guess a subset of questions that I can imagine is like, were there many like this? Like, could you choose between many options like Vitess, and then you're like, well, there's 20 more. What would have happened if you had to build this from scratch? Like, mm-hmm. Would Slack would have been viable, or you would have like lost 2 years? So I don't have a specific question, but I guess you get the sense for like what I'm trying to ask. Yeah.
No, this is a really great question. And this these, I don't know, like I think are like fundamental moments at this certain stage of the company, right? So this was 3 years ago. Like we were seeing like these challenges, and literally like similarly to how it took me maybe like 3 months to build the confidence on the system that I just described, we spent like 6 months doing research of like what is the system that we can adopt. Because what you said, like this is where we store our data, like this is critical for our business. So what we do here, it will impact years. It was a decision that was, I don't know, it's 3 years now, like we're just finishing the migration, and this will be the technology that we will have for years to come. So at that time, it comes to defining like what are the requirements that we had for the system. And we went out and we started to look what options we had. And we found things like CockroachDB, you found things like Cassandra. At that point also, a spanner from Google was something that was starting to become popular. And we evaluated all those options. But when we weighed those options against our requirements, none of them like tick all the boxes. And Vitess was doing that. So of course, at the end of the day, it was a calculated risk. We didn't know if Vitess was going to work, but of all the technologies that we saw around, it seems that it was the one that was closest to feeling like all those boxes that we needed. And actually, like in hindsight, we've been reflecting a lot recently, like what happened if Vitess didn't exist? I think that, like, luckily, when you are in a business that is thriving, you will find a way. Like, we were going to be able to engineer a way out of that problem. But what I would like to argue is that I think we will have started something that was going to be very similar to Vitess, because the requirements were the same. And then when you start with those same set of requirements that you're trying to solve, highly likely you're going to converge to similar solutions. And I think I'm very invested in this project, but what I'm seeing right now in the industry, that people that wants to use MySQL and they want to scale MySQL and do it in an horizontal way using sharding, Vitess is starting to become kind of like the de facto in the industry to do that, which means that science that is probably the right abstractions and the right way of solving the problem.
Yep.
Does that answer your?
Yeah, it certainly does. Thanks. That's pretty cool. We have 1, 2, 3, like 4 people asking, 5, and we have 15 minutes. So I think we can kind of get all the questions in. The questions are written pretty. There's more coming. Okay, we'll see. We'll do our best. So people, I'll start unmuting people. Be fast on your questions and kind of succinct, and same. Try to do like a fireside answers. Like you're some guru that can answer everything with 5 questions, with 5 words, Rafael. Okay, let's do our best. If we go a little bit over, that's fine as well. Let's just try. Okay, I'm unmuting you, Julio, first. So you can ask. I think you have like 2 questions in one.
Okay, yeah, I have a couple of questions. So this layer on top of Vitess to support the legacy shards was just used for the migration step. After that, it is out of the system?
Yeah, that is correct. Like we built, like all that part of like BT Chobol and like the framework to do the reads. That's only while we are in this process of like moving it. But once it's done, it's just as any other vanilla shard on Vitess. And then from the operations perspective, it looks and acts as any of other of our Vitess shards. So that was like that was one of like the things that we wanted to achieve. Like right now, operating like the 2 kind of like systems it's a burden for our data stores teams. And also, I didn't share, but like for most of this time, like this was a 10 people team, supporting thousands of database servers. So in 10 people, having to build the knowledge to support the 2 systems and know how to operate them at scale, it was a big cognitive overload. So our goal was like, once this is done, it's just one system.
Okay. And the other one is that you talk about this diff analysis that you did with Vitess and the legacy shard. Was that done on every migration on the queue of shards?
Yeah. So it was. So there was one stage where we did like really in depth, you know, and we took like this sample of shards and we analyzed literally every single query and every single diff, because by definition, because there is lag, there could be diff from time to time, you know, because if you are trying to, in certain parts of the application, the semantics were read after write. So the application was writing and then expecting to read that data right away. And there were cases where in Vitess, that data was not replicated like yet. So we spent a lot of time convincing ourselves that the times that we did see diffs, it was because of that. And once that confidence was built, every time we migrate a single shard, we do two kind of like diff invalidation. One that is kind of offline, where we build, and that's also a very interesting project in this migration, that in Vitess, we implemented a process that syncs the replication between the two databases to know that you will have like a consistent snapshot of the two data sets, and then compare all the rows there and check that, do we have all the data that we think we have? And that is kind of like offline, if you like. And we do that for all the migrations. And then we also turn on this dark reads framework, and we check that from the application. It's looking like more or less okay. And there we are not that concerned at this point. It's just like 30 minutes. Is it routing to the right shard? Are the diff within a certain criteria that we believe it because of lag? Yes, boom, move it.
Thanks, Rafael.
Okay, awesome. I'm unmuting Jesus, and if you can, Julio, mute yourself. Perfect, thanks. I'm muting Jesus for his question.
Okay, thank you. So would you recommend to use MySQL for a large app, or would you recommend using another one like Postgre? Do you think MySQL scales well, or are there better options?
I think nowadays, and of course, like limiting the space to, if you are interested in relational databases, if you want to use MySQL and then you have a technology like Vitess, yes, like MySQL will be able to scale for large applications. And the way that you scale it is by having like shards. Like you will have like many MySQL clusters. Having said that, I think depending on the size of your company, operating a system like Vitess could create also a significant burden in the operations team. So there are out there right now solutions like Aurora for AWS that provide MySQL that can scale horizontally to a certain degree. It cannot scale as much as Vitess. As a matter of fact, I know of companies that are starting to adopt Vitess in front of Aurora to scale like even further, but using something like Aurora could be like a really good start, in my opinion.
Okay, thank you.
Michael, I'm looking for you on the chat so I can unmute you. Okay, you're on mute. Go for it.
Okay, thanks first of all for sharing this with us. I would like to ask the following. During the 3 years of the migration was going on, Slack has introduced new features and some of other were improved. So here is my question. How do you integrate a new feature on Vitess, and if the new feature impacts in the migration plan?
Yeah, this is a really great question. And it was a challenge, no? And I can divide it like in two categories. When it was a this at all, those cases were straightforward, because what we did is that we sent it directly to Vitess. They created their tables in Vitess and they were implemented in Vitess from scratch. However, let's say what happens where we were trying to improve an existing feature and it was in the middle of a migration. Let's say we were improving certain things about how threads work, and the tables that supported threads were behind the message model, and we were trying to move those. What we did there, and the way we solved this problem, and we actually had like, I think we made some mistakes along the way, because at the beginning, many of the tables, we were trying to migrate them from the data stores team, and we didn't have the domain knowledge to understand like these nuances, and especially if like new features were being added. What we did is that as we started to learn more about how we were doing like this process, we created teams that were from data stores and then from domain experts of those features, basically the teams that own those parts of the application. And we worked tightly with them. And so they were really involved in the pieces of the migration, but then they also had the context to understand, oh, we are developing these new features, and we know that we're migrating this table to Vitess, so we need to make these changes as well as we are doing like as we're developing this feature. And that's why like the first 3 years, I said that it's not really a migration, it was a re-architecture. It was taking like each single table, understanding the domain, and mapping it to what it will mean to move this table to Vitess. And as part of that process, it also involved, oh, this feature is coming. Okay, how we plan for this feature while this is also in flight. And yeah, that was very, very challenging, because that part, I would say, is maybe like where the intersection is just not technical. It's a lot of like how you, as an organization, you are able to collaborate effectively in these kind of projects.
Awesome. Thank you.
Hi, ma'am. I'm muting you. Sorry that I skipped you before. Go for it.
Okay. Thank you. First, Rafael, thank you for your talk, for sharing your experience. It's always great to listen about real experience. And I'm the oldest here in this group, so I come from the times where consistency in databases was very, very important. You cannot conceive a small inconsistency. And the time, you know, that ACID transactions and that stuff. So I'm concerned about, you said that you had this master that you allowed some small inconsistencies. And then you said we built this other system that is not, it's also had some inconsistencies, but it's no, you know, we had that before. So perhaps you could explain how much inconsistency and what kind of inconsistency, because I understand that in applications like Slack, well, if there's small inconsistency, it's not a problem. Mm-hmm. But you know, for a bank in China that has to manage transfers of money, perhaps you cannot allow that inconsistency. So perhaps tell us about that.
Yeah, no, I think that's also like a great observation and great points. And I think like philosophically, like it starts from that part. Like for us, having like small inconsistencies is not a problem. And we optimize to being available. So we prefer to run into inconsistency than having the system being down. In the opposite, like, right, like when you are in banking systems, you prefer to be down than allowing inconsistencies to happen. So I think that's kind of like the design principle that is behind this. And then to go specifically into the kind of inconsistencies that we found, they were normally when, because these two systems are replicating from each other and both are accepting writes, what happens if there is a network partition for a blip of a second and you send a write to, let's say, the right pair, and the application thinks that that write didn't made it and thinks, oh, this write fails. Our logic automatically tries to write the same statement on the other side. And in fact, it was sent to the right side. What happens in that scenario is that replication like breaks immediately between those two databases, because when you write on the left side, then the right side tries to replicate to the other side, and it says, oh, I cannot write this because this row already exists, for instance, if it was an insert. And when that happens, we basically build tools that tell us replication broke, this is the diff, and with the years, because most of the times it was cases where it was maybe like just an insert that was into size, it was just like a duplicate key error, we started to build tooling, oh, this is safe to just ignore this one and take the other one, they are the same. If we run into situations where it was an update and then the update was actually different values, at some point we say, okay, we pick one of the two and this one wins, and we accept that it could be that someone will go one day and look at the message and then, oh, this was not the edit that I did. It was actually this, and it changed, literally. But we accepted that fact, and we were kind of like okay with that because we said we prefer availability and we are optimizing for that. And then the other kind of like trick that we did that is very specific to MySQL is that many of our statements use this clause where on duplicate key, do this. So kind of like the application, when it ran into inconsistencies, it healed itself for most of the normal cases.
Thank you.
Cristobal, I'm muting you first, and if we have time, Raul will get you in, but we'll see what happens. Go for it, Cristobal.
Hi, I would like to know if you could go a little bit more in depth talking about the data model, for example, for messages. Maybe like what are the, I don't know, like most common queries in the infrastructure. I'm curious, for example, if you do ordering anywhere, where do you do your ordering? And how has scaling the infrastructure influenced how your storage in any way, your data modeling decisions?
So I think I can start with the last part, but like it influences like entirely. You know, like for messages, for instance, in the legacy system, it was charted by team, and then that means that if you have a team, again, let's say like you have Amazon, and then Amazon is creating hundreds of thousands of messages per day, that chart was growing at a way faster rate than other charts in the company and in the system. So when we were in the process of migrating messages to Vitess, we said, okay, like what model makes sense to migrate this data in a way that our infrastructure can scale horizontally and more evenly as time passes. So in that process, we analyze, okay, what is the model of the messages table? And I think the big insight is that for messages, when you think of a message in Slack, messages are in the context of channels, right? Like you're in a channel, you're writing messages, and then you're sending messages in that channel. So it seemed that the right model to chart messages was using channel ID.
Yeah.
And we look at all like the most common like queries for this table, and we saw that in fact most of the time you will have the channel in context, and it was like really rare that you were not going to have that. And as a matter of fact, it was like so rare that it was only in like maybe like admin pages or in some pruning jobs where you were doing like data retention, and then in that context that you didn't care about the team and you were just like deleting like messages in bulk. But like for like what was the application itself, channel like made sense. And then that was what we did. Like when we moved this, the queries stayed the same for the most part, but they changed to be charted by channel. And then what that means is that it doesn't matter the size of the company, channels will, like messages will be distributed evenly across channels in the cluster. However, there is one pitfall on that. Like what happens if then you have a single channel that is that big and that active that doesn't fit in a single chart? Like that is something that could happen, but that one, like we said, like, oh, we'll wait. That problem, it will be a problem for Rafael's of 5 years from now. And I think that's kind of like, yeah, it's like very, very like tightly, and we try to think, okay, what's the model that would allow us to scale for, optimize for, I don't know, like 5 or 10 years using like the sharding key and like the kind of queries that we do. Then in terms of like ordering, I don't know if I have like a really specific answer for that, but I think, I don't know, if you look like that window of a channel, like the normal like query is order by dates, and then there is always like another like really important part of our model is what we call like the channel cursor, that is like where you are in this channel. So normally the clients get all the data with a certain buffer before that cursor, and then after like what is live is done through different systems, that is what we call like real-time services, and then those just get like pushed in. And going to the database to kind of like get the historical data happens more like in a cold boot, or when you see that your Slack client reloads. And yeah, I don't know, like I don't have off the top of my head like all the query patterns, but like high level, it's like they have channel presence, and then that's the important thing for us in how like we scaling when it comes to the databases. Does that answer your question?
Yeah, perfect. Thanks.
Yeah.
I just was a little bit curious.
Rafa, so we're 2 minutes over. Can we, and if the answer is no, it's perfectly fine, but I think if we spill over 7 more minutes, I think we get one more question and the wrap up. Do you have 7 more minutes or you have to run?
I'm good, like I have time.
Okay, Raul, get your question in, and then we'll wrap up, and I think we'll do it in the next 7 to 10 minutes at most.
Okay, thank you. And thanks, Rafael, for your talk. So my question is about the application code, because you mentioned that while you were comparing like the answers from this new topology with the previous one, you noticed differences, and you had to change application code to be able to work with, I imagine, both at the same time, because you cannot forget the current topology you are using. Mm-hmm. So I imagine the complexity increased in that case, in terms of the application code. But after the migration is over, was there any difference, like significant difference in terms of the application code, like more complexity, or just about the same as before?
No, after like we don't do any changes like after, like the complexity stayed the same. And I think, yeah, this is also like a really like good point. And the cases, like when we started this project, we said, if we run into many cases, I don't remember like the exact number, but like one of like the hypotheses that if we need to change the application a lot to do this migration as well, it's not worth it, because it's all this process plus trying to change the application to work this way. So it was like very, very specific cases where we saw diffs because of the difference of MySQLs in the two systems. They were all down to MySQL version like differences, and it was just a few cases, like literally I think it was like 5 queries that we had to update, and it was something like silly, like specifically the order. If you don't provide an explicit order clause in MySQL 5.6, it changed the ordering criteria to MySQL 5.7. So the diffs that we were seeing were actually because the data was being returned in a different order, and not because the data was in fact different. So again, yeah, like it was only very specific cases where we had to do this. And if we had run into more of those, it was going to be a no-go for this project. And it was, okay, this strategy didn't work. It was one of like the big assumptions that we had in order to invest and to continue to invest in this strategy.
Okay, thank you.
Okay, I think we're 6 minutes over, so it's not too bad. Rafa, this was amazing. Thank you so much.
No, thank you for having me.
No, this is incredible. I recorded it. We can take a look at later. Perhaps the recording is useful to you. Perhaps not. We can just look through that, and I'll probably try to edit a little bit and try to like put in like some better formatting. So if you want to share it, then that's useful for you. Thank you to everyone who came. Super special thanks to the guys who asked questions. I really appreciate that. I think it went well. I kind of liked it. If anyone has feedback as Rafa said on his presentation, send it my way. I'll make sure he gets it. If someone has feedback on the formatting and this thing we just did, this is the first one, so we have nowhere to go but up, hopefully. So tell us how to make it better, and we'll do so. I like this space. I think it's pretty neat. I think if we can get more people doing cool stuff in Silicon Valley, connected to like good engineers across LATAM, only good things can happen. So I'm grateful we did this. Thank you to everyone, Rafa especially, again. Thank you, man. And if anyone feels like helping Venezuela with code, go to Code for Venezuela. There'll be some onboarding, and you'll see Rafa on the other end of the tunnel of the onboarding. So go there if you need that. Anyways, thanks Rafa. Thanks everyone.
Thank you. Bye.
Take care, man.